Okay, so this is a video that I'm really excited about. So it's going to be broken up into two levels, right? The first level is going to be the main focus is to determine what is the value of 0 to the power of 0. That is the main focus of this video. So there's two levels. The first level is going to be elementary level, meaning that we're going to be using maybe high school level work. And then the second level will be A-level mathematics, meaning we're going to be dealing with limits and L'Hopital's rule and all of that stuff. So let's just focus on elementary level. Okay, so in order to actually determine how to approach this type of question where 0 to the power of 0 is equal to something, let's consider the following, right? We have 1 raised to the power of 0 and we have 2 raised to the power of 0. Let's focus on those two. 1 to the power of 0, and hear me out, can also be written as 1 to the power of 1 minus 1, right? Because this exponent here will just be equal to 0 if you say 1 minus 1. And now we can also write this like this, using the exponent laws of subtraction, where we can say that the base raised to the power of 1 divided by that base raised to the power of 1, right? So we're going to have the top minus the bottom over here, meaning we can use that exponent law here. Okay, great. Now, the next thing we're going to be looking at is going to be, I apologize, you know what, I'm just keeping that there. What we can also see is this can also be written as 1 divided by 1, right? Which is just equal to 1. Okay, so now we're actually getting somewhere where anything to the power of 0 is equal to 1. But let's just prove that by looking at 2 to the power of 0. If we can break 2 to the power of 0 into 2 to the power of 1 minus 1, using the same logic over here, we can write this as 2 to the power of 1 divided by 2 to the power of 1, which is equal to 2 divided by 2, because anything to the power of 1, it stays the same. Which 2 divided by 2 is just equals to 1. Can you see how we're getting that logic? And you can even try, for example, 64 raised to the power of 0. You'll still get the same thing. Now we're going to focus on 0 to the power of 0. So let's do the exact same thing. We take 0, we're going to say 0 to the power of 1 minus 1, which is just going to be equals to 0 to the power of 1 divided by 0 to the power of 1, which is equals to anything raised to the power of 1 is just the same. So it's going to be 0 divided by 0. And what you can see is here is that we are going to get, because we have something divided by 0, and if you want to make reference, if you still think that anything divided by 0 is infinity, I recommend looking at my other video where I prove that anything divided by 0 is undefined. So because we have something divided by 0, it's going to be undefined. Okay. So therefore we have proven that 0 to the power of 0 is undefined. But that is elementary level. Let's actually look at A-level mathematics. Okay, so let's consider the following, right? We have 0 to the power of 0. And what do we note about this number and this number? These two are exactly the same to one another. So what we are going to do is we're going to rewrite this as x to the power of x. Because if we plug in 0 to x, if we say x is equal to 0, that will mean that we're going to plug in 0 into the x, meaning we're going to have to also plug it into the exponent. That'll give us exactly what is over here. So what are we going to do? We're going to just take it a little bit further, right? So I'm going to just quickly keep it as x to the power of x over here. But then we're going to take the limit as x approaches 0. Meaning that if we directly substitute into this function over here, which is x to the power of x, we'll get a certain answer, right? Now, what we note is if we directly substitute, we'll get 0 raised to the power of 0, right? And then this is just going to be equals to, and we just proved that it was undefined, right? But remember, we're working with limits, and we're not looking at where it is exactly on that point. We're looking where it is approaching that point, right? Which is 0, where x is approaching 0, not at 0. So let's remember our rule where we say if the limit as x approaches a from the left hand side is equal to the limit as x approaches a from the right hand side, therefore this will exist basically. So the limit then therefore will exist. But if they're not equal to each other, the limit will not exist. Therefore we have to say that the limit as x approaches a, which is from both sides, will not exist. It doesn't exist. basically. That's only if this is true. But let's go further into the detail over here. Okay. Now, what we're going to look at is the following, right? We have the limit as x approaches 0 of x to the power of x. But let's just try and write it as a function, right? We know that the limit of x as x approaches a of any function, right? This could be represented as a function. So what we are going to do is we're going to let f of x equal to x to the power of x. But we want to actually just break it down further so we can have some type of function, right? So we can actually represent it as a function. So we want to write it as an exponential function. So let's just try and simplify it a little bit more so that we can have some type of exponential function. So what we can do is we can also write this as e to the power of ln of x to the power of x. Because if you remember your logarithmic rules, if you have e to the power of, if you have, let's say, for example, ln of anything, right? Then, in order to get rid of this, okay, let's say we have ln of x is equal to 1. And we want to take Euler's number on both sides. So we're going to say that it's going to be e raised to the power of ln of x is equals to e to the power of 1, where this, due to our laws, this will fall away. And then we will have just the value in the brackets that becomes a part of the equation, which is x is equal to e to the power of 1, which is just e, in our case here. So that is what we're doing. But what you can see is that we are writing e to the power of ln of the function, basically. Meaning that it will eventually fall away, and it will, if we do simplify from there, these will eventually fall away, and it'll give us exactly what is here inside of the bracket. Okay, cool. Now that we have established that, we can also use our exponential rules where we have the natural log of x to the power of n, and then this will just be equal to n multiplied by the natural log of x, where the exponent will just go outside of the natural log. Okay, so that is another law that we can go over as well. So that is what we're going to do here. We can see x is an exponent here, so we can just take that out as a coefficient. So we're going to have e to the power of x multiplied by ln of x. And now what you can see is we have a composition of functions. And now from here, I'm just going to show you what the graph of f of x is equal to e to the power of x times ln x looks like. Okay, so what we notice here about this function is the following, right? So if you were to put in f of x is equal to, or if you were to put in e to the power of x times ln x into our graphing app, you would get the following function, right? Over here. And what we can notice, even if you also put in x to the power of x in the function thing, you'll get exactly the same thing. It'll also follow the exact same trajectory as that. Obviously, I'm not so good with my drawing, but it's absolutely fine. So what I want to show you over here is on this function, what do we see over here? X is not less than 0, right? It's always greater than 0. But is it equal though? Now the thing is, remember that if we let x equals to 0, right? As if it was our y-intercept, right? Our y-intercept is where we let x equal to 0. If we let x equals to 0, we will get something along the lines of undefined, right? It is undefined at x equals to 0. So therefore, the asymptote is just the y-axis. X equals to 0 is our asymptote, our vertical asymptote of this function. But now what we want to show over here is that, well, we already see that it's undefined. So we don't really need to work out the limit as x approaches 0 from the right-hand side, because we can see there is no function going from the left-hand side. So clearly, from this information over here, there's no use of doing L'Hopital's rule. You can do L'Hopital's rule to actually check out this value. So what I want you to do, maybe just for extra practice here, e to the power of x ln of x. Remember what we had here? We're going to take this function over here, because remember, it's the limit of a function. So we're going to just replace the function with that over there, thus giving us this over here. So maybe for homework, if you can, do this and see what it gives you. It should give you some value, but I'm not going to spoil it. Okay, I'm joking. It's going to be 1. It's going to approach 1. You can clearly see it's going to approach 1 from the right hand side, but it won't be equal to 1. The reason why I know it is because I've done it already. And I want to see how you do it, and then see if you can get the answer 1. If you do get the answer 1, let me know in the comments down below, and then I'll give you a heart. So, yes, what we are seeing is that because we don't have anything on the left from the left-hand side, we can say that therefore the limit as x approaches 0 from the left-hand side is undefined, right? Okay, wait, I forgot to say. Of e to the power of x times ln x is going to be equals to undefined. And then because of that, obviously, if we are to try and compare this to the right-hand side, so the limit as x approaches 0 from the right-hand side, it should give you an answer of, so I'm going to say of f of x, which is exactly that one. If it's equal to 1, we can clearly see that the limits does not exist, because it's not equal to one another. So therefore, we can also prove over here, from using limits and a function, that 0 to the power of 0 is going to be undefined. How cool is that, man?